Hello, this is Mr. Stein, and in this video, we are going to look at the graphs of relations and functions. After you're done this lesson, you should be able to write down the domain and range of a relation or function in set notation. You should be able to use the vertical line test to check if a relation is a function. You should be able to tell when data is continuous or discrete. All right, let's take a look at the vocabulary and the basics. Domain. The domain is the horizontal axis on our graph. So if we have a graph here, this is our domain. In an ordered pair, our domain value comes first and our range value comes second. The domain is the independent variable. And oftentimes our domain value is time. Our range, on the other hand, on our graph, our range is our vertical axis. Our range is the second value in an ordered pair. A range is a dependent variable. What the range value is depends on what the domain value is. All right, set notation. Set notation is something that you need to learn how to use. Sets have these curly braces at the end. A basic set is just a list of all the possible values. So we draw a curly brace, cat, cow, dog. A set of animals with 3 letters in there. Name. Here's another set. 1, 4, 9, 16, 25. This is the set of all the perfect squared numbers less than 30 and greater than 0. So these are just sets where a set is just a list of values. Now, sometimes a list of values is impossible. Sometimes we need a whole bunch of numbers. So here is a set for all of the natural numbers. So the set of all natural numbers, these are all the numbers from 1, 2, 3, 4, 5, 6, ... Now, what if I wanted to write the set of all even natural numbers? Well, there's a way to do this. This is the even numbers. So our even numbers, E, such that an even number is equal to 2 times some other number, where this number is an element of the natural numbers. Whew. Our variable is E, and E is equal to 2 times some number, where that number is some part of the natural numbers. This is a way to write the set of all even numbers. When n is equal to 1, E is equal to 2. When n is equal to 2, E is equal to 4. When n is equal to 3, E is equal to 6. So this set contains all the even numbers. Now, we're going to use this a lot. And it's going to look like this. Our domain value x, and x has to be greater than or equal to 0. X could be any real number, so it could include decimals. This type of set notation we are going to use a lot. What would this set look like? Well, x would be equal to 0, then 0.000001. Every number larger than x would go in this set. We can't even write them down. We can't even start to write them down. It's too many. So we are going to use this form of set notation a lot. All right, the vertical line test to test for a function. You can see Notability is just having a difficult time on my iPad. Vertical line test. A function is a relation where every domain value, so here's a domain value, has exactly one range value. So we put that in, we draw the vertical line, it crosses the graph once. Our domain value of 1 has a range value of 1. There is no other possibilities. Anywhere I draw a vertical line, on this graph, it only crosses exactly once. Vertical line, it only crosses once. Every domain value has exactly one range value. So this graph passes the vertical line test. So it's a function. Does our second graph pass the vertical line test? Well, let's look here. At 1, our domain value is right here. It's 1. Now let's draw a straight up and down vertical line. Passes it once, passes it twice. Our domain value of 1 has the range value of 2. But our domain value of 1 also has the range value of -2. This graph does not pass the vertical line test. It is not a function. Domain values go to more than one range value. Our domain value of 1 goes to 2 separate range values. Therefore, it's not a function. All right, we're going to take a look at these basics. We're going to turn these number lines into an answer into set notation. Assume that the number line represents the variable x. All right, so let's take a look at our first number line. In this one, x is bigger than, but not equal to 2. It's not equal to 2 because there's a dot there. And x could be any number on this number line. It could be 2.5, 2.7, any number. So x is a real number. So to write this in set notation, this is for the variable x, such that x is greater than 2, comma, and x could be any real number. That's how you read that. Let's look at our second one. In our second one, x is less than or equal to 1. I'm going to choose a different color for our second one. And again, it could be any real number. So this would be our variable x, such that x is less than or equal to 1, and x is an element of the real numbers. Now, how would this look if x wasn't an element of the real numbers, but x could only be integers? I'm going to do this one in red. On the graph, it would look like this. You would just put dots at every integer and then have a little arrow going that way. And for the red one, this would now be x such that x is less than or equal to 1, and x is an element of the integers. I always use z for integers. You could use capital I as well. All right, let's look at the next one. The next one we have x in a range. So we always write our smallest value, -3, is less than or equal to x, and I put the equal sign because it's a solid dot there, and x is less than 5. And because it's a solid line here, it could be any real number between -3 and 5. So this set is all of our values of x such that x is between -3 and 5, and it could equal -3, and x could be any real number in there. All right, our last one. Do the same thing. Let's take a look at our 2 is less than or equal to x, which is less than or equal to 6. So x is anywhere in that range. So our variable is x such that 2 is less than or equal to x, which is less than or equal to 6, and x could be any real number between those two. Now again, I'll show you what this would look like if it was just integers. So if it was just integers, it would just be dots at all of these spots. And we would write it like this. X such that 2 is less than or equal to x is less than or equal to 6, and x is an element of the integers. So then it would just be dots. We call that discrete. The solid line up here is continuous. The dots are discrete. All right, hopefully you should have an idea now of writing domain and range in set notation, using the vertical line test to check if a relation is a function, and you should have starting to have an idea of when the data is continuous or discrete. We'll look at the